Applying Gauss's law, example 2.4 using cylindrical symmetry. All right, so previously we talked about the electric field generated by a sphere of charge Q. When you have a sphere, it sounds natural that you would use spherical symmetry to draw a spherical Gaussian surface. Right. Let's talk instead about cylindrical symmetry. So I have a long cylinder. All right, that long cylinder carries a charge density. This is example 2.4. I have a long cylinder that carries a charge density that is proportional to the distance away from the axis. Okay, so no longer necessarily a constant charge density. Find the electric field inside of this cylinder. Okay, so I have a axis. All right, I can define whatever that axis is. I have a long cylinder. All right, here's my cylinder that's centered around that axis. And that cylinder has a charge density, rho, so that means it's a volume charge density, that is proportional to the distance away from that center of that axis. Okay, so here is the distance s, right? I guess that's the maximum distance. I shouldn't draw that. Just draw some distance s away from that. Okay. And I'm looking for the electric field inside my cylinder. All right, so let's draw a Gaussian surface. Well, let's write Gauss's law in integral form first. So I have all of the flux going through some surface is equal to 1 over epsilon naught Q enclosed. Now, my goal here is to pick a surface that makes this dot product easy. For cylindrical symmetry, we're going to use a cylindrical Gaussian surface. I'll draw that with red. All right, I'm going to pick some region of space. Like this. I'm going to say that it is some distance L long, and that surface that I'm evaluating the electric field at is a distance S away. Okay. Now, let's go ahead and do the right part of our Gauss's law first. So we have Q enclosed. Let's find what Q enclosed is. Q enclosed is going to be equal to the integral of that charge density over that region of space. All right, I have charge density, rho ks, so it's my integral ks. All right, now I'm going to call it primed, specifically because that's the prime coordinates. I guess technically I should have d tau prime here. That's where the charges are, so those are prime coordinates. And then I need to build my infinitesimal volume element in spherical or in cylindrical coordinates. Okay, that is s prime, ds prime, d phi prime, dz prime. And I'm integrating over that whole volume. All right, so I have three integrals I need to do. The integral over z, I guess I'll just draw it up. That becomes k. I'll do 3 integrals s prime squared, ds prime, d phi prime, dz prime. All right, dz is going to go from 0 to L. That's the length of my Gaussian surface. Phi is going to go from 0 to 2 pi, and s prime is going to go from 0 to s. That's where I've arbitrarily drawn my Gaussian surface to end, right? And specifically, it's asking for inside of a cylinder, so I know that my Gaussian cylinder will always be inside of my physical cylinder. So I do that. I'm left with, right, the phi gives me a 2 pi, the z gives me an L, 2 pi L K, and I'm left with 1/3 S cubed. That looks about right. Okay. So, what direction are these electric fields pointing? All right. My choice here is to make my dot product of my integral as easy as possible. Well, the electric field points radially outwards. So, because I have patches on here that also point radially outwards, that dot product becomes just the magnitudes of those. So I'm left with the integral over that surface of my magnitude of my electric field, where I've assumed that that electric field is pointed radially outwards. I've defined it, rather. And the magnitude of my dA component. That electric field, because of the symmetry I've chosen, is constant at all points in the surface, so I can pull it out of the integral, and I'm just left with dA. And that becomes the surface area of that curved surface, which is E 2 pi SL. All right, so that's all the flux leaving the curved surface. But what about the flat surface? Right? I could have tried to define my surface as one of these two caps. All right. Well, if the area vector is pointed out and my electric field is pointing this way, those are perpendicular to each other, and the component of those dot products gives 0. All right. So this full closed surface integral is really the curved surface plus the components of 0 that are associated with those ends. All right, so then I combine my two expressions that I've accumulated. I have E 2 pi SL is equal to 1 over epsilon naught 2 KL pi over 3 S cubed. I think that's right so far. 2 pi's cancel, L's cancel, and I'm left with E equals K over epsilon naught 3 S squared. Okay, that's right. Now, I don't have a direction associated with that, but I need to go ahead and add that based on my definition that led me to make this dot product so simple. Right. I said that the electric field is radially outwards, so I can't forget to add that in the end. Notice one thing, what does this expression not depend on? It doesn't depend on L anymore. All right, so I could have drawn this Gaussian surface as big as I wanted, or as long as I wanted, and as long as it remained inside of my object, I could have picked any length for my Gaussian surface.